Hello and welcome to this lesson video where we will learn about scrapers, their types, and the approach to analyze a scraper's typical production cycle. This video covers the shown four learning objectives. Scrapers are designed in favorable operation condition to perform the whole typical cut-to-fill cycle by itself by loading the soil, hauling it, dumping it, and returning back to the cut area. Scrapers are like the transformers. Scrapers have the mechanical means in their big ball or tummy to load themselves without the need for the help of a loader or excavator. Scrapers are good for intermediate lengths of cut-to-fill holes in the middle between the economic haul distance of dozers and trucks. However, scrapers are not superior to the task-specific equipment in their own playfields, so they're not better than excavators in loading or faster than trucks in hauling. Let's watch a video to see how the scrapers work. As we have seen in the video, we see that the scrapers follow the typical load, haul, dump, return, earth moving cycle. We will add to these steps two more steps. Turning at the cut, and turning at the fill area. So we can model the scraper operation at 6 total steps. Let's see how to estimate each of these steps. The video showed us the mechanism used to load the scraper, which is done by lowering the scraper bowl and opening the apron gate while the scraper moving forward. The soil is loaded like you scoop ice cream. This piece in the back is called ejector, stays still during the loading step and will be the main part to dump for the scraper, be the main part in dumping, like we'll see later. Once this desired scraper load is achieved, the bowl is lifted and the apron is closed. The scraper load time is determined based on the desired scraper load. The more time you allow the scraper to load, the more soil is scooped into the scraper bowl, but it's not linearly proportional. For example, 0.5 minutes allow to load about 86% of the scraper payload. Doubling this time will result in 14% load increase, and almost tripling it will add 3% more load. So the loading time is variable and needs to be determined ahead of the operation. But based on what? There is an optimal loading time that needs to be calculated for the scraper to achieve the maximum production for a specific haul distance. Spending less or more time than this optimal load duration will result in lower production rates. This chart here shows that the longer the haul distance, the more the time the scraper is allowed to load. As the haul distance increases, the total cycle time increases, the less impact the load time it will have in production, and the more positive impact the increased load time will have on the scraper production rate. Also, the load time is dependent on the scraper mechanical power system. Scrapers can be powered by only the front axle or both front and rear. The front single powered axle provides less power to cut through the soil and load it in the scraper bowl. The double tandem powered axle provides more push force and makes the loading easier for the scraper. As such, for the same loading time, the tandem power will be able to load more soil than single powered. As for all earth-moving equipment, we need to relate its payload to the soil bank volumes that are being cut. Heaped capacity of the scraper can be achieved by using sideboards, but unlike trucks, the soil in a scraper bowl is not completely in a loose state. As the scraper cuts through the soil, the new soil entering the bowl compacts the soil already in there. So realistic payload estimates require increasing the load factor by about 10%. This assumption doesn't apply to a type of scraper called elevating scrapers, which we'll see later in this lesson. Let's illustrate this point with an example. We need to calculate the corresponding bank volume of the soil that's being cut with a 17.5 cubic meters scraper. The soil load factor is 0.8, which we remember from the early lessons of this class, that the load factor relates the bank and loose volumes of the soil. However, the soil is not really loose. So we adjust the load factor by 10% to increase it from 0.8 to 0.88, which results in an increased bank volume of 15.4 bank cubic meters. We are done with the loading time. Let's see how to estimate the haul and return times. In motion, the scraper bowl is lifted and the apron is lowered to hold the soil load. For both hauling and returning, we can estimate them by rough judgment or by using the performance charts of the pull. of the scraper. We will need to use the Rempel chart if the scraper experiences positive resistance. If the scraper experiences negative resistance. And use retarder chart. Going back, we will need to use the Rempel chart if the scraper experiences positive resistance going upward. And use the retarder chart if the scraper experiences negative resistance, or what we call assistance. Please refer to the other lesson video on machine power to learn about machine power and performance charts. Now let's see how dumping time is estimated. In dumping, the ball is slightly lowered, the apron is raised, and the ejector moves forward to push the soil out of the ball. This table provides the recommended dump times for different scraper sizes and power system. Of course, we see that we need more dumping time for larger scrapers, and we can also see that less timing is needed for double tandem powered scrapers due to the direct power provided to the ejector. Lastly, the two turning times are estimated based on the site conditions. But here are some suggested values for turning times at the cut and fill areas. More time is estimated for the cut area turning because the scraper spends more time in adjusting to the desired cut lane, and also to wait for a dozer to push it in the pusher loaded scraper operation, like we'll see very soon. So here's a summary of the steps of calculating the scraper cycle time. In detailed scraper cycle estimates, the haul and return times are broken down to segments of acceleration and normal speed and deceleration for more accurate time estimates. For accurate production estimates, it's recommended to account for acceleration and deceleration times before and after the scraper haul and return trips. Adding up all these times will result in the cycle total time. As such, the scraper ideal production will equal its cycle production, that's calculated by dividing the scraper haul capacity over the cycle time. Then the effective production rate is calculated by multiplying the cycle time by multiplying the production ideal rate by the expected efficiency. This effective production rate can be used to estimate the operation duration by knowing the total haul quantity of the scrapers and determining the number of scrapers. The cycle time calculations we learned so far apply to self-loading scrapers. Let's see other 4 types and variations of the scrapers we covered before. Let's watch this video of the pusher loader cycle. The pusher-loaded scraper is a regular scraper that needs the help of a dozer, a pusher, to give it a nudge during the loading period and help it accelerate for the whole trip. We need to model this operation as a two-link system that depends on the existence of a free scraper and a free dozer to load. This requires a similar analysis to that we covered in the trucking lesson. Let's watch this video of the push-pull scraper operation and how it compares to self-loading scraper operation. Push-pull scraper operation is also a two-link system in which two scrapers help each other in loading. This is done through block and bale to allow two scrapers to safely connect together and help each other in cutting and loading the soil. The block is in action when the rear scraper pushes the front scraper, while the bale latch makes the front scraper pulls the rear one to help it in its loading. This approach helps in saving the need to have a dozer on site to help the scrapers, especially if you don't have enough scrapers to make them cover the dozer and make it 100% utilized. Elevating scrapers used built-in chain elevators to lift the soil from the cut surface inside the bowl. It's very useful in hard, tough soil, but it adds more weight to the scraper. Also, you sacrifice the scooping compaction mechanism that you would have in the regular scraper type. However, elevating scrapers can help to avoid extra help from a dozer or another scraper. Finally, an auger scraper uses an auger to help reduce the resistance of already loaded soil against loading more soil in the bowl. Similar to elevating scrapers, the auger adds more non-productive dead load to the scraper. Here is a cross-section view of the scraper bowl with an auger inside. I hope you enjoyed this lesson, and see you in the second lesson on scrapers to learn how to design economic scraper operations.